Hello again, grade sevens. In today's lesson, we are going to talk about three different methods of energy, thermal energy or heat transfer. Those methods being conduction, convection, and infrared radiation. Learning outcome is to explain how heat is transmitted by conduction, convection, and radiation in solids, liquids, and gases. And we will start off with conduction. Conduction is the transfer of thermal energy through an object as a result of collisions between vibrating neighboring particles. Okay, let's explain this using this illustration. So in this illustration, you have a heat source. This could be like the flame of a Bunsen burner. And this here is some kind of a solid object. And what we're doing is inside the solid object, we're showing some of the particles that make up the solid. Now, what's going to happen is the particles that are on the end of the material that's closest to the heat source, they're going to absorb some of the thermal energy from that flame. When they absorb thermal energy from that flame, and we're talking about particles in a solid, they're going to start to vibrate. So they'll vibrate back and forth, vibrate back and forth, vibrate back and forth, vibrate back and forth, etc. What happens is, for example, to look at the top row here, when this top row starts to vibrate back and forth, it then collides with its neighbor, which is this middle particle right here. And then when it collides with that neighbor, it transfers some of its energy over to that one, and then it starts to vibrate back and forth. And all these ones vibrate back and forth as well, because they receive energy from the other particle due to the collision. And then finally, the middle particles, when they vibrate, they're going to collide with the ones on the far right, and it's going to cause these ones to start vibrating. They start vibrating, start vibrating, start vibrating, start vibrating. And then the overall effect is you're transferring heat, and heat is a transfer of thermal energy, from one side to another. And specifically what you're doing here is you are transferring energy from the side that is warmer, or the hot side, to the cold side. And that's the process of conduction. So again, conduction is the transfer of thermal energy through an object, and this happens because of collisions between vibrating neighboring particles. I should point out, though, that as you go from this collision to the next one to the next one, you start to progressively lose more and more energy. So the particles that are near the heat source would always be vibrating faster than the ones on the right-hand side. But nonetheless, you still are transferring some of that energy over to the far right-hand side. One thing about conduction is that this can only occur in solids. In order for conduction to occur, the particles have to be close enough to each other so they can actually collide. Well, that's no problem for a solid, because in solids, your particles are closely packed together. So if one particle starts to vibrate back and forth, no problem, it collides to the next one. But if we look at a liquid or a gas, the particles are further apart. So this guy can vibrate back and forth all at once, but if there's too much space between it and its neighboring particle, then it's not going to hit it. And if it can't hit that particle, it can't transfer any of its energy over. And another note is that metals are identified to be good conductors of thermal energy. So good heat conductors are ones that are very effective or efficient at transferring thermal energy from one particle to another. Now, to compare that with an object called an insulator, Insulating objects can also be solids. So you can have two particles that are very, very closely packed. The problem with insulators is that even if you give the particle in an insulator energy, it can barely vibrate. And if it can barely vibrate, it doesn't do a good job of hitting its neighboring particle. And if it doesn't do a good job of hitting its neighboring particle, then you can't transfer heat. So not all solid materials are good conductors of thermal energy. Some metals, and some metals that come to mind might be like aluminum, copper. I think nickel is okay at transmitting thermal energy. And some solid materials are not good at transferring thermal energy. And I believe steel is an example of that. But you don't always want your materials to be good conductors of heat. I think steel is used to make up a lot of those I-beams that you see in like large skyscrapers. Again, an I-beam has like a cross section kind of like this here. Well, the better something is at conducting heat, the more it can expand and contract. If you're looking at large skyscrapers, you don't want the materials expanding and contracting all the time. So this might not be a good thing. So steel, which is a good insulator, might be a better choice if you're looking at an actual structure. The second method of thermal energy transfer is one that is called convection. Convection is the transfer of thermal energy from one place to another by means of a moving fluid. Okay, so let's look at this example. So what I have is, let's go to the red color. So I have a Bunsen burner flame. And I have a beaker that's on top of a wire gauze. It's attached to a retort stand. And I have the Bunsen burner placed underneath the bottom of the beaker. These little tiny circles just represent some of the particles that make up the actual water we're looking at. So let's try to trace out what happens with convection. When you heat this fluid up, the particles near the heat source are going to gain energy. They're going to move faster, they'll get warmer, and then they're going to move away from the heat source. So that's these little guys right here. So these little guys, because they're close to the heat source, are going to gain energy. And when they gain energy, they're going to move away from it. More energy that you gain, the more capacity, I suppose, you have to like move away from your heat source. So they're going to gain energy. And because it's a liquid, the particles can actually translate and they're going to move. So they'll move like somewhere up here. What then happens is the cooler particles, so the ones that are further away from the heat source, well, they're going to lose energy. And when they lose energy, they're actually going to sink. So they're going to drop back down here. What you can see happening is something that's called a convection current. So let's just try to trace this. So we take one of these particles here, it gains energy, and it moves up and away. You take one of these colder particles, one that's up here, and then it moves, it sinks, it loses energy, sinks and goes down here to the heat source. Then it gains energy because it's close to the heat source and goes up. So these particles just keep going around in a big cycle, or a big current is what we call it. So as this process repeats, we refer to this as being a convection current. And this is something like some examples would be like an air current. The other big one is we actually talked about this back in the Planet Earth unit of study. So in the Planet Earth unit of study, we talked about how convection currents are responsible for the movement of our plates. So again, we have our plates here, which form the lithosphere. And then below the lithosphere, we have the particles that make up our asthenosphere. Again, the asthenosphere is a layer that's kind of like partially melted. It's got like the consistency of taffy. And then underneath that, we have the really, really hot core. So you can think of like the hot core as being like this humongous heat source. And then what this does is, if you look at the particles that make up the asthenosphere, so take one particle here. So what would happen to it? Well, the particle close to the heat source would gain energy, okay? Gain energy, move away, rise up. Then when it's up here and it's further away, it loses energy, and then it sinks. And this process just keeps happening over and over again. But as these particles start to rub against the actual plates, they can cause the plates to move. So in this case right here, I might be able to show the plate movement. So as it goes up here, it might like rub against the plates and cause this plate to go towards the right. So perhaps there could be a converging plate boundary in that situation. So that's another example of a convection current. It turns out this can only happen in liquids and gases. And the reason being is that in order for the particles to actually move up and then move back down, they need to undergo a form of motion that's called translation. So translation is a form of motion from point A to point B. Particles in a solid like a brick, they're kind of locked into place. Like, yeah, they can vibrate back and forth, they can spin, but they can't move around unless the person actually picks the brick up and moves it. So conduction can only occur in solids, and convection can only occur in liquids and gases because you need that translational form of motion. Our final method of energy transfer is, well, I'd say it's electromagnetic radiation. We're going to be more specific. We're going to refer to it as infrared radiation. Infrared radiation is the transfer of thermal energy outwards from a source in every direction in the form of an electromagnetic wave. Let's use the sun as an example. Okay, so here's the sun. Infrared radiation from a heat source will be transferred in every single direction. So this direction, towards the left, down, towards the right, up and to the right, up and to the left, down and to the left, down and to the right. So from a heat source, we transfer infrared radiation in every direction, and it travels in the form of an electromagnetic wave. So instead of drawing it, the direction of motion as like a straight line, we could have it just like kind of like moving in a little bit of a wave type shape. Now we need to clarify a little bit about what is an electromagnetic wave. Well, electromagnetic waves, they're energy carriers. It's just a carrier of thermal energy. Okay, it's like the sun. When the sun emits infrared radiation in the form of an electromagnetic wave, energy is being carried from its electromagnetic wave from one point to another. Electromagnetic waves have the ability to move across empty space, which is obviously why we can feel the infrared energy or thermal energy can be transferred from the sun to us on the Earth. They also move really, really fast. They move at a speed of 300,000 kilometers per second in air or a vacuum. When I say a vacuum, so air would be like a region where if I drew like a representation of air with particles, you have like a few particles around, okay? Lots of space between them. A vacuum, like the vacuum of empty space, would have nothing. There are no air particles whatsoever. 300,000 kilometers per second is what we refer to as the speed of light in air or a vacuum. And it's exceedingly fast. Like if you want one way to think about it, if you looked at how fast light could travel, it could travel around the Earth 7.5 times around its circumference in 1 second. 7.5 times in 1 second. Like that is a crazy fast speed in terms of how fast electromagnetic waves can move. Now, if you go into a different area, like if you had the electromagnetic wave go into water, it would slow down, but it would still be moving really, really, really fast. This infrared radiation tends to get absorbed by darker objects and reflected by lighter ones. I don't know if you ever had like the misfortune of like getting into a vehicle on like a really, really hot summer day where it's like plus 30 degrees and the seats are like all black leather, and like the instant you touch it, it like burns. And that's because surfaces that appear darker, like black surfaces, they tend to absorb all of that infrared radiation, which is why it's so hot when you touch it. Lighter objects, like objects that appear white in color, they tend to reflect that. Thermal energy. So that's why you see astronauts in white spacesuits. When you're in space, you don't have the Earth's atmosphere to protect you. Or if you're on the moon, same thing. You don't have an atmosphere to protect you. So all this infrared radiation from the sun is like coming at you full on. These white spacesuits tend to reflect a lot of that infrared radiation, which enables the person in the suit to be somewhat safe, aside from the fact they're in space, which is essentially trying to kill you every instant you're in there. In terms of what objects emit infrared radiation, everything. Like an object, like you emit infrared radiation. A block of ice, even though it's really, really cold, it emits infrared radiation. A canister of, I guess, liquid nitrogen, which is pretty close to absolute zero, it would emit infrared radiation. So any object that's above your absolute zero temperature emits infrared radiation. Just some objects are going to emit it a lot better than other ones. And yes, humans do emit a lot of infrared radiation. In fact, there's some security cameras that in like museums or buildings that are specifically set up to detect the presence of of infrared radiation. And if the infrared radiation, like a certain areas, like suddenly just spikes up, it's a good indication that there might be like a thief in there, and then the alarm gets set. Okay, so that's it for this lesson, and you can complete the assignment called Methods of Thermal Energy Transfer. And in the next lesson, we'll talk about energy transfer systems.